Welcome to Selection Sathi. Today we will learn about hashing and hash tables, one of the most important data structures in computer science. Hash tables provide average O of one time for search, insert, and delete, making them essential for gate CSE and coding interviews. Let us start with the hash function. A hash function maps a key to an index in the hash table. The simplest method is the division method, h of k equals k mod m, where m is the table size, ideally a prime number. A good hash function distributes keys uniformly across all slots. The multiplication method is another approach, h of k equals floor of m times k times a mod 1, where a is a constant between 0 and 1. What happens when two keys hash to the same index? That is a collision. Chaining is the simplest collision resolution technique. Each slot in the table stores a linked list of all elements that hash to that index. Insertion is O of 1 since we just prepend to the list. Search takes O of 1 plus alpha on average, where alpha is the load factor n over m. In the worst case, all keys collide and search becomes O of n. The alternative to chaining is open addressing. Here, all elements are stored directly in the table with no linked lists. When a collision occurs, we probe for the next empty slot. Linear probing checks slot h of k, then h of k plus 1, plus 2, and so on. It is simple but causes primary clustering. Quadratic probing uses h of k plus I squared, reducing clustering. Double hashing uses a second hash function for the probe step, giving the best distribution. The load factor alpha equals n divided by m, where n is the number of stored keys and m is the table size. For chaining, alpha can exceed 1, but performance degrades as chains grow longer. For open addressing, alpha must stay below 1. Typically, we rehash when alpha exceeds 0.7. Rehashing means creating a new table roughly double the size and reinserting all existing keys. This costs O of n but happens infrequently, so the amortized cost per insert stays O of 1. Let us insert the keys 15, 22, 37, 15, 29, and 8 into a hash table of size 7 using h of k equals k mod 7 with chaining. 15 mod 7 is 1, 22 mod 7 is 1, 37 mod 7 is 2. 15 again goes to slot 1, 29 mod 7 is 1, and 8 mod 7 is 1. So slot 1 has a chain of 5 elements, 15, 22, 15, 29, 8. Slot 2 has just 37. The load factor is 6 over 7, approximately 0.86. Now linear probing. Insert 10, 22, 31, 4, 15 into a table of size 7. 10 mod 7 is 3. Slot 3 is empty, place it there. 22 mod 7 is 1. Slot 1 is empty, done. 31 mod 7 is 3. But slot 3 is taken by 10. Linear probing, try slot 4, it is empty, so 31 goes to slot 4. 4 mod 7 is 4, taken by 31, try 5, place there. 15 mod 7 is 1, taken, try 2, it is empty. Final table, empty, 22, 15, 10, 31, 4, empty. How fast is search in a hash table? Consider a table of size 10 with 5 keys. so alpha equals 0.5. For chaining, a successful search takes 1 plus alpha over 2, which is 1.25 comparisons on average. For open addressing with linear probing, the expected number is about 1 over alpha times the natural log of 1 over 1 minus alpha, which gives approximately 1.39. Both methods give roughly 1.3 comparisons, which is essentially constant time. When should you use a hash table versus a binary search tree? For search, hash tables give O of 1 average, BSTs give O of log n. For insertion, hash tables again win with O of 1. But here is the catch, hash tables do not support ordered traversal. If you need elements in sorted order, a BST gives you in-order traversal. The rule of thumb, use hash tables for fast lookups, and BSTs when you need sorted or range-based access. Some quick tips for exams. First, always choose a prime number as the table size, far from powers of 2. Second, chaining is simpler, but open addressing has better cache performance. Third, rehash when the load factor exceeds 0.7 for open addressing. Fourth, in gate questions, count the number of collisions and probe sequence length carefully. For more concept videos like this, download the Selection Sathi app. Like and subscribe. Thank you.